Continued from part 1, we have the shear matrix, which is a matrix that produces a shear transformation. But what is a shear transformation? Turns out it's not the easiest to describe verbally, so you have to see it for yourself. The matrix 1101 is a shear matrix, and this is what it does. What we see is all the vectors above the origin were moving towards the right, and all the vectors below the origin were moving towards the left, and the way they move was actually parallel to the x-axis. So overall the rectangle was slanted into a parallelogram. In 2D, there are 4 directions we can apply a shear transformation, 2 different ways we can shear in parallel to the x-axis, and 2 ways in the y-axis. It's also notable to mention a property shear matrix have, which the transformation preserves the area of the object despite changing the shape, which forms a distinction with the scalar matrix from earlier, which preserves the shape but changes the area. A 3-dimensional shear is kinda hard to describe. Personally, I'd like to imagine there's a plane slicing through the origin, and there is a direction associated with this plane. All vectors moving parallel to the plane, while slanting towards the direction. Maybe that was not the best angle to observe a shear transformation in 3D, so let me change the orientation of my camera a little bit. And for every combination of this plane and direction, it would have its own corresponding shear transformation matrix. Next, the orthogonal matrix. This one is very important for chapter 2 and 3. It's a square matrix. Every column vector is a unit vector, and they're all orthogonal to each other. Let's dissect the definition a little bit. So, what is a column vector? Basically, if we vertically slice through the matrix into columns, each column is a vector. This is the reason why some people say matrix is a collection of vectors. For a column vector to be a unit vector, it means the magnitude is 1. In our case, the length of the arrow is 1. For a counterexample, the red arrows on the screen are not unit vectors because they're too long. How about orthogonal? So the formal definition for orthogonal is when you take the dot product between 2 vectors, the number you get is 0. And when the dot product is 0, visually it actually translates to the 2 vectors being perpendicular to each other. This one is orthogonal matrix. We can quickly verify the 2 column vectors are unit and orthogonal. What kind of transformation does it have? Wow. A perfect rotation. No scaling, no stretching, no shearing, no reflection, but a pristine rotation. You might say, come on, it's just a rotation, there's nothing special. But it turns out finding the correct direction to rotate is a gateway to unlock all complexity with linear transformation. And it just happens the transformation an orthogonal matrix produce is always a rotation to some degree. Inductively, a 3x3 orthogonal matrix produces a rotation in 3 dimensions, and you can also rotate around the z-axis now. Actually, now's a really good time for me to once again emphasize the idea that matrix-to-matrix multiplication is nothing but a composition of sequential transformations. Suppose I tell you orthogonal matrix A produce a rotation around the x-axis by 60 degrees, and matrix B produce rotation around the z-axis by 45 degrees. If I multiply those 2 matrices together to get a matrix C, what do you think C is going to do? Well, let's see. Firstly, around x, and immediately around z. Since our matrix C is a composition of the 2, like you guessed it, it encapsulates the 2 sequential transformation, but in just 1 rotation. If you had noticed, I really tried to punctuate the word sequential just now, because suppose we reverse the sequence of the 2 rotation, namely z first, then x, we actually get something different than the original composition. Look at the position of the orange cube. It's different. This is actually an example to prove matrix composition or matrix multiplication, is not commutative, which is saying matrix B times A is not always equal to A times B. Projection matrix. Actually, before defining a projection matrix, we need to understand what is a subspace. And just like all other definitions in linear algebra, the definition for subspace is pretty abstract. At the moment, allow me to just provide you with some examples. In 2D, a line crossing through the origin is a subspace of R2, and this line is infinitely long. In 3D, a plane crossing through the origin is a subspace of R3. I'm only showing you a small region of the subspace here, but in reality, you should imagine the subspace actually spread to infinity. For every subspace that exists, our computer can calculate its corresponding projection matrix, which would move every vector outside the subspace onto the subspace. Let's take a look at the projection matrix of this blue line here. After the projection transformation, every single dot has been compressed onto the line. How about the projection matrix of this plane in 3D? Yet another very similar vibe of compression. The reason why this is called projection is because every vector always moves to its closest point on the subspace. For example, the vector 2, 1 is currently outside the blue line, and its closest point would be here. Applying the projection matrix would move our vector 2, 1 exactly over there. And this is true for every single vector outside the subspace. As targets of projection matrix, they all move towards their closest landing spot. And fun fact, if some alien civilization destroy our solar galaxy by compressing us into a lower dimension, this kind of transformation is similar to a projection matrix. The very last, but not the least, we talk about the idea of inverse. So far, we have seen a lot of different matrices and therefore many different transformations. All those transformations were moving our vectors to new coordinates. But what if I don't like a particular transformation I had? Maybe it distorted my image a little bit. I just want every vector to go back where they originally came from. Is there one matrix that can untransform the previous transformation for me? Unfortunately, the short answer would be no. There isn't one matrix that does the universal untransformation. But for every matrix you're interested in, our computer can calculate its inverse, which is another matrix that is capable of that particular untransformation. For example, the matrix which scale, its inverse matrix unscale. The matrix which reflects, its inverse reflects back. The matrix which rotates, its inverse rotates back. The matrix which shears, its inverse unshears. Or this matrix here, not sure what it did, but its inverse matrix restores all vector back to the original. Notice, when you apply a matrix and then you apply its inverse, it's like nothing happened, just like the identity matrix. This is the reason when you multiply a matrix and its inverse, you always get the identity matrix. When you compose the two transformations together, you get the transformation of no transformation. However, some matrix cannot be inverted. The zero matrix and projection matrix from earlier cannot be untransformed. It actually kind of makes sense visually, because vector has been squashed from a higher dimension down to a lower dimension. There is a loss of information. After a long journey, we have went through all those cool matrices. So what exactly is a matrix? Does matrix intrinsically carry a visual value? Frankly, not at all. Everything I did was only a very artificial attempt to make sense of matrices. You could say matrix visualization is just another human construct. This moment, I'd like to reference a quote from my favorite author. He was asked whether his readers could interpret the symbolism in his novel the way he intended to convey. He answered, "The books belong to the readers now, which is a great thing because the books are more powerful in the hands of my readers. I think this is true for Matrix as well. The interpretation of Matrix belongs to whoever is using it." For a student who studies circuit, Matrix is just a tool to solve system of equation. Personally, I still have some PTSD from Gaussian elimination. For a probability student, Matrix is the best representation of a Markovian process. For data scientists, a matrix is just a manifestation of a table, which facilitates data analysis. And for the deep learning folks, matrix is just another Python function, which takes a vector as input and returns a vector as output. And this list really goes on. Perhaps there isn't the definition of matrix, but only interpretations of matrices. Then, what is so good of the visual interpretation? Firstly, I think it provides us with intuition about matrix transformation on vector. And secondly, computer graphic is a direct extension of this. Thirdly, the one I like to elaborate on personally, which is a very important topic of matrix decomposition. There are matrices out there whose transformation is so perplexing I cannot easily articulate. And there are matrices taking vector from higher space to a lower space. Is there a possibility we can re-express those complicated transformation into a sequence of simple transformation, such as rotation or scaling? And that's where we're heading towards next in Chapter 2, what Professor Gilber Strang calls the king of all matrices, and let you and me go spectate the spectacular spectral decomposition. See you there.